The inspector's requirement for ground rods at both the meter and the sub-panel stems from several crucial aspects of electrical safety and code adherence. Firstly, safety is paramount. A ground rod establishes a low-resistance pathway for electricity to dissipate into the earth. This safeguard is critical in preventing electrical shocks and mitigating the risk of fire. In the event of an electrical fault, the ground rod acts as a conduit, channeling errant current away from the electrical system and safely into the ground. This rapid diversion of fault current minimizes the potential for damage to equipment and, more importantly, protects individuals from hazardous electrical exposure. Secondly, code compliance plays a significant role. Many jurisdictions mandate the installation of ground rods at both the meter and the sub-panel to align with the National Electrical Code, or NEC, requirements. The NEC emphasizes the importance of proper grounding for all electrical systems to ensure safety and reliability. Meeting these code requirements is not merely a formality, it is a fundamental aspect of ensuring the safe and compliant operation of the electrical installation. To elaborate on improving the grounding system, installing a ground rod at the sub-panel enhances the overall grounding by creating a secondary route for electricity to reach the earth. This redundancy is particularly beneficial in locations characterized by poor soil conductivity or prevalent electrical noise. In areas where the soil is not conducive to effective grounding, the supplemental ground rod provides a more reliable path for fault current dissipation. Similarly, in environments with significant electrical interference, the additional ground rod helps to stabilize the grounding system and minimize the impact of noise on sensitive equipment. While installing a ground rod at the sub-panel may not always be strictly necessary, it is generally a prudent measure. The relatively low cost and straightforward installation process make it a worthwhile investment in bolstering the safety and dependability of the electrical system. By providing an additional layer of protection against electrical hazards and ensuring compliance with established codes, the inclusion of a ground rod at the sub-panel contributes to the overall integrity and performance of the electrical installation. Grounding is a critical aspect of electrical systems, ensuring safety and proper function. It involves creating a low-resistance path for electrical current to flow back to the source in the event of a fault. This path is typically achieved by connecting the electrical system to the earth through grounding electrodes, such as ground rods. The primary purpose of grounding is to protect people and equipment from electrical shock and damage. When a fault occurs, such as a short circuit, the grounding system provides a path for the fault current to flow back to the source, tripping a circuit breaker or fuse and disconnecting the power. Without proper grounding, the fault current could flow through a person or object, causing electrical shock or fire. The National Electrical Code, or NEC, provides detailed requirements for grounding electrical systems. These requirements cover the size and type of grounding conductors, the installation of grounding electrodes, and the bonding of metal enclosures and equipment. Adhering to the NEC guidelines is essential for ensuring the safety and reliability of electrical installations. Ground rods are a common type of grounding electrode used in residential and commercial electrical systems. They are typically made of copper or copper-clad steel and are driven into the ground to provide a direct connection to the earth. The depth and number of ground rods required depend on the soil conditions and the size of the electrical system. In areas with high soil resistivity, multiple ground rods may be necessary to achieve the required grounding resistance. The grounding system consists of several components that work together to provide a safe and effective path for fault current. These components include the grounding electrode conductor, the equipment grounding conductor, and the bonding jumpers. The grounding electrode conductor connects the grounding electrode, such as a ground rod, to the electrical service panel. The equipment grounding conductor provides a path for fault current to flow back to the source for metal enclosures and equipment. Bonding jumpers are used to connect metal parts together to ensure that they are all of the same electrical potential. Regular inspection and maintenance of the grounding system are essential for ensuring its continued effectiveness. Ground rods should be checked for corrosion and damage, and the connections between grounding conductors and electrodes should be inspected for tightness and integrity. Any damaged or corroded component should be replaced promptly to maintain the safety of the electrical system. In addition to protecting against electrical shock and fire, grounding also helps to reduce electrical noise and interference. Electrical noise can disrupt the operation of sensitive electronic equipment such as computers and audiovisual systems. A properly grounded system can minimize the effects of electrical noise, ensuring reliable performance of electronic devices. There are different types of grounding systems, each designed for specific applications. The most common type of grounding system is the grounded system, in which the neutral conductor of the electrical system is connected to ground. This type of system is used in most residential and commercial buildings. Another type of grounding system is the ungrounded system, in which the neutral conductor is not connected to ground. This type of system is typically used in industrial applications where a high degree of reliability is required. Proper grounding is not only essential for safety, but also for the proper operation of electrical equipment. Many electronic devices rely on a stable ground reference to function correctly. Without proper grounding, these devices may experience malfunctions or even be damaged. The NEC requires that all electrical equipment be properly grounded, regardless of whether it is connected to a grounded or ungrounded system. This requirement ensures that all metal enclosures and equipment are at the same electrical potential, minimizing the risk of electrical shock. When installing a grounding system, it is important to follow the manufacturer's instructions and the requirements of the NEC. The grounding electrode conductor must be sized correctly and installed in a way that protects it from damage. The grounding electrode must be driven deep enough into the ground to ensure good contact with the earth. The connections between grounding conductors and electrodes must be tight and corrosion resistant. Regular testing of the grounding system is recommended to ensure that it is functioning properly. A ground resistance tester can be used to measure the resistance between the grounding electrode and the earth. The resistance should be below a certain value, as specified by the NEC. If the resistance is too high, it indicates that the grounding system is not functioning properly and needs to be inspected and repaired. Grounding is a complex topic, but it is essential for anyone working with electrical systems to have a basic understanding of its principles and requirements. Proper grounding can save lives and prevent property damage. It is always best to consult with a qualified electrician to ensure that the grounding system is installed correctly and meets all applicable codes and standards. The inspector likely wants to see that you have two methods of grounding. The first ground rod at the meter provides a direct path to earth for the service entrance. The second ground rod at the sub-panel provides an additional path to ground and helps to ensure that the sub-panel is properly grounded. This is especially important if the distance between the meter and the sub-panel is significant, as the grounding conductor may not be sufficient to provide adequate grounding on its own. Here are some additional details about grounding that may be helpful. Firstly, the size of the grounding electrode conductor is determined by the size of the service entrance conductors. The NEC provides tables that specify the minimum size of the grounding electrode conductor based on the size of the service entrance conductors. Secondly, the grounding electrode conductor must be connected to the grounding electrode using a listed connector. The connector must be suitable for the type of grounding electrode being used. Thirdly, the grounding electrode must be installed in accordance with the NEC. The NEC specifies the minimum depth and spacing requirements for grounding electrodes. The NEC section 250.50 covers grounding all grounding electrodes together. All grounding electrodes that are present at each building or structure served shall be bonded together to form the grounding electrode system. Where a grounding electrode is present, it shall be bonded to the grounding electrode system. Interior metal water piping shall be bonded to the grounding electrode system. The location of the grounding electrode is also important. The grounding electrode should be located as close as possible to the service entrance. This will help to minimize the impedance of the grounding conductor and improve the effectiveness of the grounding system. In addition to ground rods, other types of grounding electrodes can be used, such as ground plates and underground metal water pipes. Ground plates are typically used in areas where it is difficult to drive ground rods, such as rocky or paved areas. Underground metal water pipes can be used as grounding electrodes if they meet certain requirements, such as being in direct contact with the earth for at least 10 feet, or 3.0 meters. Grounding is also important for sensitive electronic equipment, such as computers and audiovisual systems. These devices are often susceptible to electrical noise, which can cause them to malfunction or even be damaged. A properly grounded system can help to reduce electrical noise and improve the performance of sensitive electronic equipment. In addition to the NEC, other codes and standards may also apply to grounding systems. These codes and standards may vary depending on the location and the type of electrical system being installed. It is important to check with the local authorities to determine which codes and standards apply to the specific installation. Grounding is a critical aspect of electrical safety and should not be overlooked. Proper grounding can protect people and equipment from electrical shock and damage, and it can also improve the performance of sensitive electronic equipment. Always consult with a qualified electrician to ensure that the grounding system is installed correctly and meets all applicable codes and standards. Regarding the specific wire sizes mentioned, the 2/0 copper conductors are likely adequate for a 200 amp service, but it's crucial to verify this against the ampacity tables in the NEC, specifically table 310.16. The table provides allowable ampacities of insulated conductors rated up to and including 2000 volts, 60 degrees Celsius through 90 degrees Celsius, in free air, based on the conductor's insulation type and installation method. The #4 copper grounding electrode conductor is also likely appropriate, but again, confirm its adequacy according to NEC table 250.66, which dictates the size of the grounding electrode conductor based on the size of the service entrance conductors. The separation of the neutral and ground at the sub-panel is correct for sub-panel configuration, as it prevents circulating neutral currents from flowing through the grounding system, which could create a shock hazard. The 200 amp main breaker at the sub-panel serves as the main disconnect for the panel and provides overcurrent protection for the circuit served by the sub-panel. The use of a mobile home meter-based disconnect in the pole is also a common practice, providing a convenient and accessible point for disconnecting power to the house.